Hi guys, we will be doing the parametric, that is the iterative study of fiber orientation on a composite rectangular plate using the ANSYS. For this we will be using the ANSYS software. In that ACP module will be used and static structural analysis module will be used and also the model analysis will be used. And let me tell why we are using this. Initially we will be modeling a rectangular plate using the ANSYS ACP, and then we will be making it as a laminate. And what is a ply, what is a laminate, what is a lamina is already uploaded as a video in this channel, and you can look into it. And then the orthotropic carbon fiber properties that will be defined. Multiple fiber orientations, that is the parametric study that is about to be done here, and it will be defined as a parameter, design parameter. These will be iterative one here, and static structural will be used to study the stiffness, like how the deformation occurs, and for each iteration that we are going to do in the fiber orientation. And also the model analysis will be used to get the natural frequencies of each iterative rectangular plate. Yes. The objective is to quantify the influence of the fiber orientation, what we are going to change in the rectangular plate, and how it influences the structural response and dynamic characteristics is what we are going to learn now. Now let's say we are going to iterate three different orientation cases here, and fiber orientations, in the sense what I'm going to say is let's say this is a case 1, and say for the case 2 we are going to use 5 plays actually. So in the case 1 there are 5 plays. This is the case that what we are going to repeat and do and iteratively. If we do it iteratively, the thing is, one complete simulation setup will take approximately 15 minutes. If you are well with ANSYS ACP, static structural, and the model analysis also in the PC. Fine. So running each fiber orientation a separate model will require repeating setup steps, also the managing multiple files over approximately 40 minutes of manual work. But if we use the parametric iteration, we will be using a single model and single file. With reduced setup time, you are going to get maximum deformation and natural frequency for all the three cases in a single file. This is what we are going to do now, and yes, this will enable faster comparison and efficient design and evaluation, right? Like so, yes. I have opened this ANSYS, and yeah, initially we'll be using the ANSYS ACP here. In the component system, ACP pre will be there. Pre is what we are going to drag it here, and in the engineering data we can choose the material. So I don't want this structural steel, so I'm deleting it, and I will be clicking on engineering data sources, and I will be using any composite material. The composite material will be here. Yes, when you click on it, yes, we can get the composite data that is available in the ANSYS here, and we can choose any composite material, and I'm choosing carbon fiber 230 GPa, the basic thing. Yes, and when you click on here, it will be added to the ANSYS for further processing. Yes, again I'm going and clicking on the project, and the geometry will be edited using space claim. And yes, we have opened the space claim, and I'm going to draw a rectangular plate. For that I'm using the rectangle here, and define rectangle from center, so it will start from the center, and then this is the center, and then here we can define the rectangle. I just want to give a dimension, so I'm giving 50, that is the length, and when you give tab it will move here, and this will be 20. This is what I'm going to give. And yes, when you click enter and end sketch editing, we will be getting the surface face. We will be getting the surface of the rectangle, and then using pull we can pull it, but for this analysis we don't need. Yes, we have created, and that's all in space claim, and then we will be double clicking the model, and yes, as we have defined the geometry well, it will be tick, and then next our process will be in model. Yes, we got the geometry here, and we are going to apply the material. So this thickness is not of use, so we can define any thickness here. This is a dummy thickness, and the original thickness of this the carbon plate will be defined. We will be defining in the ACP in few minutes. Okay. So I'll be changing the units as well, and we need to define the material as well here. So the material what we chose is carbon fiber 230 GPa. Machine is a process of defining a continuous geometry. Yes, the rectangle plate is a continuous geometry, right? So that will be divided into a finer number of small elements that will be connected by nodes. So the elements nodes I will be telling you, so that the numerical methods can use the governing equations to solve. It can be any result. When the mesh is much finer, when it is very good, the more accurate results is. So for this I'm using 1 mm element. So when we give meshing, this is the meshing what is done on the plate, and the continuous structure is converted into a structured mesh. And now when you select this, you can select the node. So yeah, this is the node what is said in the uh, PPT. Yeah, I have told you now, like connected by nodes. So each element is connected by node. This is the node, and this is what we call as an element. Yes. So the mesh is done. So we will be going into ACP pre-setup. Mainly to solve this, one thing I need to say is like when you to utilize your complete capacity of your system, you need to control this. So for my system, it is actually to check the course. You need to go to performance, and you need to check the course here. My system has 8 cores actually, but by default ANSYS will have only 4 cores. So to utilize it completely, you should give 8 cores. This is a trick to use your complete PC's capacity. And yes, the ACP is getting started. Yes, we got it, and initially it will be there like nothing is there, but when you click on the center button and move it, and you can see the plate that is in the model. Yes, and the materials is already there, what we have selected in the engineering data. Define the unit actually, so we will be defining a unit. I want it in MPa, so it will be in mm. Initially it was there in meter, so converting it into mm. We can go to the fabric and edit this. So selecting this material, I'm giving 0.2 mm for one ply. Fine. Yes, for one ply. I will be telling you the composite basics. It is already in another video what I have already made. I will make it as a short. And now this is a fiber what we have chosen, the carbon fiber. The matrix which is in a liquid shape, that will be mixed with it, mixed with the carbon fiber to make the composite structure. Fine. So this is a single ply. When you mix fiber plus matrix, it is called a ply, and the ply is also called as a lamina. So the carbon fiber is already there, and the epoxy resin is what we are going to use uh, in real. Fine. And then so this is what we made as this is called as a lamina. And then when we keep multiple plies like this, it is called as laminate. So we can give n number of plies with n number of angles, that is up to us. We can choose the angle, we can choose the number of plies. So, and yes, like the fabric is what we have designed. We have given the thickness of the fabric, and then these things is not actually needed as of now for this simulation. And then the rosette. Let me tell you what is a rosette. A rosette, it is a local reference orientation for the fiber. Actually, the fiber is what we have chosen. It is for the single fiber and for every fiber. The thing what we need to know is the rosette is the reference direction for the fiber. We can choose we can choose the reference. The fiber can be in any direction, right? Like it can be along this blue arrow mark, it can be along this red arrow mark. So we will be defining the axis now. So origin, we are going to click on it. Yes, you can click it on anywhere, and the red arrow mark, right? Like that is what will decide the fiber orientation angle. So our fiber orientation will be along this angle, this axis, this red axis. Okay, we should remember it. And yes, we have defined the um, reference axis for the fiber. Yes, and then we will be selecting the oriented selection set. It is there because this will define the reference direction for the thickness. Yes, we have just a surface here and we need to define the thickness of the laminate. So how the plies are going to be arranged. So for that, we this arrow mark now we are not going to define the thickness around this direction. The thickness will be from down to up. So we will be selecting the point and I have selected this. So this is how the thickness is going to be made. So I'm selecting this oriented set and the row set what we have already chosen is selected here. Yes. Hope you guys understand it. And yes, I have given okay. So the thickness direction is now defined. And then we are going to go with the modeling group and we are going to create ply. Yes. The orientation selection set is will be given what we have chosen already, and the ply material will be fabric, and the ply angle is 0 degree. Yes, as I have already shown you, this ply angle is what we are going to define. This is the thickness direction what we have defined using the oriented selection set, and the ply angle we can define. So the first 1, 2, 3, I'm going to use 5 plies. So these angles is user defined. We can give it as of our own. The first ply, this is the normal surface. This angle is by default it will be 0 degree. Yes, and then we're going to copy it and I'm going to paste after this. So the second ply will have the properties and I am going to give the ply angle of 45 degree. Usually 0 degree, 45 degree, 90 degree. These are the widely used angles. I have copied these two and I'm going to paste after. So this will be created and also again we can give the paste after, but I need only 5 plays, so I'm deleting the last one. So it depends on us, like we can copy paste like anything. And for the third ply, I just want the angle to be 0 degree, it's fine. And for the fourth ply, I want it in 45 degree as it is there. And the fifth ply is 0 degree. Yes, 0, 45, 0, 45, 0 is the angle what I have defined here. And so with this, after giving everything, we are going to create the solid model. Yes, the solid model is element sets in the sense like as I told you, the element the single square is an element. So we are going to use all the elements to create the thickness direction. So to create the thickness, we are using solid model. Element sets, all elements will be used, and then we are going to give okay. Yes, it is created, and we are going to give update. Has no element set assigned. Yeah, like for this we need to create an element set. Yes, and sorry, this need to be defined. Yes, by giving okay. Yeah, which means like for all the elements the thickness direction is what we are going to define, and we have defined it. When we go update, it is getting updated. Yes, we got the we got the thickness now. As I told you, as we have defined the 5 plies, 1, 2, 3, 4, 5, the 5 plies are here. Can you see it here, right? Like 5 plies. Yes, this is the 5 plies, and the thickness is created, and show surface. When we didn't click on it, now the surface is not shown. So for this surface, the thickness is created 1 mm. How we define the 1 mm? As we have told, like 0.2 mm, 0.2 mm into, and we have created 5 plies. So each ply is of 0.2 mm and it is multiplied by 5. So together it is making 1 mm. That's all. Yes, that's all from the ACP. So and the next thing we will be transferring to static structural. So the setup, this when you drag it here, it will ask you what to transfer. The shell is the surface data. Solid is the model what we have recently made with thickness. So we need a solid model with thickness. So I'm transferring it. Yes. When you double click it, it will open. And just like when you click on this zoom to fit, it will be correctly zoomed, and the geometry is defined. Yes, from the ACP it is transferred, and here we are going to give the boundary conditions actually. Okay, to give the boundary conditions, when you normally for without ACP, we will be giving the force and we will be giving the fixed support. Yes, the fixed support will be given in when you click on this, like face will be selected, fixed support is given here, and the force is now let's say this is x direction, so it will be there in vector. So define exactly on the x-axis, we are going to give 5 Newton on the x-axis. So on the face is this. So in this phase 5 Newton is given. This is the force that we are going to give. And then the thing is, this is what we do normally, but as we are going to do parametric study, as we are going to do iterative study, this is not how we are going to define the force and fixed support. For that, we need to go to the model from the ACP model, and then we should use this edge. Let me tell you, this edge, it is where we are going to give uh, fixed support. So select this edge and click N. So it will create a named selection. Fixed support edge. Yes, and the name section is created. Click on this edge and then click N. Now force edge, and those are created, and then it is updated here. Also, we are going to update this static structural model. Opening it, we are going to use this force, and we are going and the name selection what we have already given, that came here. We just need this force edge wall and fixed support edge. And when doing parametric study, this will help. Okay, so the force, we are going to use this named selection, so we are going to change it into named selection. The force edge is what we are going to do. Also for the fixed support, we are going to use named selection. This fixed support edge, this is used. So this will work under parametric study, iterative study. And yes, we have given the force and we have given the support, and then we need the deformation. Also the stress, this is what we need. So we are going to select this. Yes. And then we are going to do model. Yes, model is dragged and selected, and also we are going to use the same model here. We need to transfer the solid composite data so that the total model will come. And for the model, we are going to do free model analysis. For the free model analysis, we don't need to give any kind of support or any kind of force. So we are going to just analysis. I need 10 modes. Yes, because as this is a free model analysis, the first 6 modes will be 0. So that will define the rigid body mode. So we won't be needing the first 6 modes, and then 7, 8, 9, 10. That is the mode we are going to consider. Done this, and I'm going to update this project. We got some issue, and let's see. And it is like this. And for the equivalent stress, we can see the stress in any ply that is here. These are the 5 plays that what I have created. For each ply also you can see the stress, but I don't want it. I just wanted to see the equivalent stress on the whole material. So I'm double clicking it, and this will be converted to layer. So now we will be seeing the whole uh, layers equivalent stress. This is solved here, and also here it got some messages. Let's see what it is. We can see the messages. Yes, it got some. We need to check the solution information. This solution information we can see here. Insufficient HPC licenses available. Yes, as I'm using the student software, it's a license issue. For the student software, I can use only 4 cores, and that is the issue, nothing else an issue. If you have got the license, you can also use the most maximum number of cores that is in your system. Yes, we have got the result, static structural, and we can see the total deformation. Yes, as we have given the forces here, this is the total deformation, and converting it to mm, this is the deformation that is happening in this system with this phase has fixed support and the force towards this side. Also for the natural frequency, you can see, as I told you, the first 6 will be 0. Yes, it is 0. 0.16 is close to 0. Yes. When you refine the mesh, you will be getting the 0 exactly, and these are the first four natural frequencies of this model. Yes. But as I said earlier, we are going to do an iterative study, but we have got for only for this initially. As of now, we have done case 1. The laminate layer what we given in the ACP is 0, 45, 0, 45, 0. This is what we have given, but we can also iterate it. So for that, to do the parametric study, to do the iterative study, we are going to convert few things as design parameter, and let's see. We will be going to ACP pre, and it's already here. Yes, these are the 5 modeling plies, right? Like here, that is parameter. Right click on the parameter and create the parameter, and this object, the object what we are going to use is modeling ply, and we are going to change this modeling ply angle. So this is converted as a parameter. Okay. Then similarly do for all the things, also for the second, and we have created the parametric study. Now we can change the ply angle. How we are going to change, I will be telling you. Yeah, the parametric set, when the parameters goes like this is an input from the ACP, we will be giving the input, and we need the output as well for each iteration what we are going to do. So total deformation with the maximum deformation, so we are going to need click on this, it will show us P. So when we give the different input, different fiber orientations as input, we will be getting the deformation. Now also we need the for model, right? Like so for model, this is it, this is there, and yes, we got the natural frequency for this as of now. So click on this, create more shape result, and then the first 6 are 0, right? Like these are 0, so we don't need. 7, 8, 9, 10 is what we need. So information, the frequency is there. So when you click on frequency, converting it as a design parameter, now we got this. So opening it, these are the input parameters. The ply angle we will be giving as input parameter. I'm minimizing it, and then the output we will be getting the total deformation and also the frequency of each. So we have given, right, for the current material. Yes, these are the inputs. Can you see? Yes, the 5 ply angles and the total deformation. These will be calculated once we give this ply angles. This is what we have initially done, and we can change the ply angle as well. That is of our need. So similarly, you can do n number of parametric study. You can give n number of fiber orientation, and then you can get the total deformation or any kind of result when you click on that checkbox. This checkbox, right? Like this checkbox, when you make it as when it is there as P, it will be there considered as a parameter, and then you can it can be input or output, and by coming here doing the parametric set here in the parametric set, it will come here. These are the inputs that you can give, and this is the outputs that what you can get. So n number of fiber orientation you can give, and the outputs you can get. Update on design points. When updating all the design points, every other space climb model ACP, this will get closed. So yes, I'm giving on show progress, you can see the results, and yes, we have got the results as of now. Yes, for each fiber orientation, we have got the maximum total deformation. When you click on this check button, you can say you can, as of now, this check button is not there ticked, right? Like so, you can see only this values only. When you click on this check button, if it is ticked, you will be getting this set as current. Now this check, so it is already set as current. Now you can see this files actually. The final files you can see. But as it is not checked, you cannot see the deformation. You can't see and the visually deformation and all, it can't be seen. So if you need to see those deformation, to see those natural frequencies in this in this mechanical and in this static structure, you need to check it. So if you do it, the size of the file will increase, because we will be getting every results what we need. So the size of the file will be increased. So or else, like, if you need only this the results, you don't need the file to, you don't need to visually see it, then you need not to check on this.